So, hi, I'm François Marion, Dronolab's team captain and representative for the AUVSI SUAS competition. We're here located at l'École de Technologie Supérieure in downtown Montreal, in Canada. And I'm glad to present to you our flight readiness review. So our team development is composed of more than 20 undergraduate students. 8 of them will be representing our team on the flight line. There's Alexis. He is our payload and electrical lead designer. On the flight line, he will be the payload operator. There's Vigitan. He is our lead mechanical designer and team captain here in Montreal. On the flight line, he will make sure that the aircraft is ready to fly. There's Frédéric. He is part of the mechanical team. On the flight line, he will be our main safety pilot. There's Tim. He developed our antenna tracking. On the flight line, he will be in charge of the communications. There's Samuel. He worked on the team organization on different events. He will be supporting the team as ground station second operator. There's Benoit. He is our software lead designer, and on the flight line, he will be our interrupt and imagery operator. There's Michaelo. He is our main CAD artist. On the flight line, he will assist the platform preparation and will assist the imaging operator. And then there's me. I'm Dronolab's team captain for this competition. On the flight line, I will be the main ground station operator. Our system can be divided in 5 major categories.
Our aircraft, the V11 Octocopter, is a UAV entirely designed by our students at ETS. Its carbon fiber frame allows the UAV to have a sturdy and robust frame while also having a lightweight core. Our UAV weighs at merely 17.6 pounds and achieves lift at under 40% of maximum thrust. We have a maximum lift of a payload of 60 pounds, which allows a maximum safe payload weight of about 12.4 pounds. So this is a decent safety factor of about 2. We have 2 platforms. The main one is identified with a green tag, as the second aircraft is an identical copy identified by a blue tag. For easy transport, we've designed our UAV as a fully foldable platform that allows any operator to move it by himself and transport it with ease.
In order to choose the propulsion system for the 2018 V11 Octocopter, we've conducted tests in a controlled environment on multiple motor and propeller. When the motor and propeller were selected, we've tested a few ESC to choose the one fitting the best our need. With the weight and efficiency analysis, we've decided to use 2 10,000 mAh SS LiPo battery. After the propulsion system selected, we then designed a custom-built power distribution board to fit in our 2018 V11 Octocopter. Based on the flight time and the task to accomplish, we've chosen the camera that suits the best our need, the Sony a6000. Since we're graded on the accuracy of the detected object, a custom PCB utilizing the flash sensor on the camera and the autopilot attitude and position data is used to geotag the picture with a sub-meter precision. We're using multi-layer of AI to find interest point in picture, if there's any, to sequence the upload to the ground station.
Our imagery software, written in C# and WPF, captures images from the drone in real time and display them to the users. The users then go through each image one at a time and find the target in them. When a target is found by a user, he then fills a form describing that target. The imagery software sends all the data related to that target to the interoperability server. This process is repeated on and on till all the images are analyzed.
Our mapping solution uses high-definition photos. In order to match with the photo size and the speed which it takes, our communication had to be fast and reliable. So we use directional antenna on the ground to get best possible communication with the drone at long distance without having interference. To control the antenna movement, we made custom antenna controlling system composed of several sensors and servo motors. Also, it uses GPS to calculate where to point.
For our ground station, we use Q-Ground Control to stay connected to our aircraft while it is flying. This way we can track a lot of information about it, like its speed, its GPS coordinates, and even the battery level. It communicates with an onboard autopilot, a Pixhawk 2, using a Mavlink protocol. So for this competition, it's very simple. We will be attempting all tasks. We are very confident in our ability to achieve the air delivery, the object detection, localization and classification, and the autonomous flight. For the obstacle avoidance task, based on our past tests, we are confident that we will avoid more than 90% of the static obstacles and more than 70% of the moving obstacles. So here at Dronolab, we take the testing part of our design very seriously. At first, we test each subsystem in our lab to make sure they all work. As soon as we have a solution that seems to work, we assemble everything, run through exhaustive checklists, and fly in our flight cage. Once we are confident that our aircraft flies safely, we take it to the field. It's there that we can test the range of our devices and the various tasks to fit the competition. Here you can see a picture of the distance and the communication between our radio and the aircraft. With this test, we can safely affirm that our aircraft can run up to 1 mile before having communication issues. We also spend a lot of time testing our aircraft in autonomous mode. This way we can modify some key parameters so that our platform completes smoothly and safely the mission. We ran more than 30 autonomous flights on our primary aircraft and more than 15 on our backup. On each autonomous flight, the pilot is there mainly for safety purposes. His job is to arm the aircraft and run the throttle to 30%. After, he switches to mission mode and the aircraft takes off, completes its mission and lands automatically. The average time spent in manual mode per flight is less than 5%. All the details of the missions are predetermined in the ground station mission planning and uploaded to the drone before it takes off. So to test the waypoint accuracy, we ran multiple autonomous missions and looked if our aircraft succeeded in hitting the target. We got a success rate of 100% during every single mission after testing our accuracy on 100 waypoints. With the UAV telemetry, we calculated the distance between the GPS positions of the aircraft and the waypoint. All of our results were within less than 15 feet, which is the acceptance radius set in our autopilot. Alright, so since the obstacle avoidance task has the greatest impact on the flyability of our drone and can dramatically affect its behavior, we started our test with a simulator. We decided to manually choose and optimize the course of the UAV to avoid any obstacle. For the moving obstacles, the operator changes the course dynamically in order to avoid them. During our test, we had more success with the static objects than with the dynamic ones. Apart from human error, avoiding static objects had a success rate of 100%. With tests and picture analysis, we concluded that the optimal ground resolution is 1 inch per pixel. This resolution is based on the minimal flight time and resolution needed by the detection and classification. In order to provide the best quality on the day of the competition, we will dynamically and automatically adjust the camera settings. We have done multiple tests in different lighting conditions and heights to make sure that we know how to adjust our camera for any given situation. To localize the object on an image taken by the aircraft, we use a software that allows a simple point-and-click operation so that when you click somewhere on the image, you get the exact GPS position of this point. This way we can quickly identify the location of each object found to maximize our efficiency. For example, here is a picture that our drone took from the field. You can see that the thumbnail window helps the user to localize the center of the object. Since the localization task is at the end of the chain, this is where the most errors are accumulated. During our test, the worst precision achieved with our software was 38 feet. To get the average precision of our localization system, we conduct tests on 22 different object positions in our field. We use a high-precision RTK GPS to reference those objects and have a comparison with our results. Based on the 132 tests, the average offset is 18.2 feet. So to detect and classify objects on the image, we use the same software as for the localization. After getting the GPS location of the object, we can quickly fill predetermined fields to give the object all of its characteristics. We decided to do this operation manually to reduce the risk of errors. The information on the object are then uploaded via the interrupt system. During our test, all images were clear enough to determine the shape, the color, and the letter, even at heights of 300 feet. The only problem we had was to determine the orientation of the shape if it was, for example, a circle or the letter O. So we've tested various systems to perform the air delivery task. Our final design is called MOB. With the system, we achieve a 90% hit on the target and a 100% open water bottle upon landing. We've tested this task more than 20 times. The payload can resist up to 5 landings, and the average distance from the target is 12.3 feet. So before leaving from our test day, we planned 3 mission scenarios as the one we will have at the competition. They were fully autonomous from the takeoff to the landing. It included capturing waypoints, dropping the water bottle, and doing a quick survey. All our missions last 12 minutes and used about 30% of our battery. The aircraft achieved to hit all of the waypoints with an average precision of 10.6 feet. The water bubble dropped at an average of 11.2 feet from the target, and the water dispersed at landing. The survey found the 3 objects that we placed in the field. Using our software, we managed to find the GPS position of each object, and comparing it to their real GPS position, we found an error of about 17.1 feet. We managed to fill all the characteristics for each object. With this test, we are very confident that we will perform well at the competition. So to estimate our score, we ran multiple full mission tests. Taking in consideration the fact that the conditions at the competition may not be as good as the one we had, we scored our performance lower than it should be. Each mission gives us a score of near 90%. So based on the full mission test that we conducted, we are confident in our ability to get a score of at least 82.3%. So this was Dronolab's Flight Readiness Review. I hope you liked it, and we're looking forward to seeing you in June. Thank you.